I already start thinking about August. Oh, is Jesus here?
My meeting has been hijacked.
Ah, Jesus, can you pause the recording?
I'm not. Oh, I see. Okay.
It's automatic.
So it's my pleasure to introduce Susanna Zimmermann, who's going to speak about finite quotients of Cremona groups.
Hi, and thank you very much to the SAC organizers for inviting me. I'm very excited to give the talk. I hope everything's going to go fine technically. So I'm going to switch out my the screen on my face because I'm going to write on the paper just to avoid any technicalities coming from having to overflow my Wi-Fi connection. So yeah, finite quotients of Cremona groups. We this is mostly joint work with Jérémy Blanc and Stéphane Lamy, and what we are going to look at birational maps from P2 over Q to itself.
Susanna, may I just say, would it be possible to bring the paper slightly lower, closer to the camera? If it's not, it's not.
I have to zoom in, but that doesn't work.
Okay, never mind then.
No,
Never mind.
I'm
It's all
sorry.
good. All good, it's fine.
So I'm going to try to write a bit bigger for the rest of the talk. I hope that will be okay then. Okay, so we're going to look at the birational maps of P2 over Q to itself and at birational maps of P3 over C to itself. So you're, instead of Q, you can choose your favorite perfect field. And we see you could choose your favorite algebraically closed field. I chose these ones for today. And so birational maps of these bases, they are of the form, they have coordinates given by homogeneous polynomials that are all of equal degree. And we can factor out common divisors, so we can assume that they have no common divisors. And in affine coordinates, they are going to be given by quotients of polynomials. So let me give you some examples. So we have, of course, automorphisms. That are PGL3 over Q and PGL4 over C. And then we have one nice map that is in affine coordinates given by 1 over x1, 1 over x2. And there's nothing that keeps us from doing this in dimension 3 as well. And well, we can also take some irreducible polynomial in one variable. And then we can construct the map x1, x2 goes to x1 alpha of x2 and x2 stays the same. We can do again the same in dimension 3. We take a irreducible polynomial in two variables. And we send x1, x2, x3 to x1 alpha, x2, x3. And we do nothing on the rest of the variables. So, right, so the over C for the plane, the Noether-Castelnuovo theorem tells us that, oh, this is a bad idea, that the automorphisms and this involution here generate the Cremona group. You just replace the Q by C. And as a consequence, we have that any curve contracted by a complex birational map of P2 is rational. And we see from these two examples here that this is clearly not true anymore over Q, because this map here contracts a curve that is birational to P1 cross alpha equal to 0 onto, well, 0 cross alpha equal to 0. Okay, and alpha can have over Q, it can have large degree. And so you're contracting a curve that is irreducible over Q, but that is not rational. It's not irreducible over C though. And the same again in higher dimension. This map here contracts a surface that is birational to P1 cross the curve given by alpha onto the curve given by alpha cross 0. So again, in higher dimension, without even changing the field, you can contract surfaces of birational to P1 cross any curve that you like. Any, really, literally as complicated as you want. And so from that perspective, actually, so what does that tell us in particular? Let me move this up a bit. Right. So for instance, it tells us that BRP2Q and BRP3C are not generated by any set of bounded degree. And by degree, I mean the degree of these coordinates of the maps as once we have divided out divisors. And the same way you can prove this for the birational maps of Pn over C for any n. So this is not restricted to dimension 3. Okay, so from that perspective, today, BRP2Q and BRP3C are a little bit more interesting than BRP2C. And the question we asked today is, does the Cremona group have normal subgroups? And the same for BRP2 over Q. I see that it's not very, I can read it a little bit because I know what I wrote. Okay, so I'm gonna write further down. And we find this question already, it's an old question. We find it already in a text by Enriquez from 1895.
Susanna, I think was that far is not in focus.
Not
I think
good.
you need to bring it slightly closer.
Okay.
Either that or my connection just dropped quality.
Start writing further down. So
Now it's better. Good, good.
This is interesting. Imagine that you have a normal subgroup of a group and you can quotient it out. You get a new group, and this new group is somehow simpler than the old group. And you can ask, is the group that we are working with as simple as it can get? So the question would be, is it simple or not? And I want to just show you with an example that it is not straightforward in dimension 2 over C already to find elements that produce, that generate normal subgroups of the Cremona group. So yeah, I'm gonna write here then. So for instance, we look at the map x1, x2 goes to 1 over x1, 1 over x2, and the automorphism 1, 1, 1, minus 1, minus 1. We have sigma h to the power of 3 is 1. You can compute this. And that tells you that sigma is a product of automorphisms of a conjugate of an automorphism. So this is contained in a normal subgroup generated by H. Okay, and we are over C. This is also the normal subgroup generated by PGL3C because it's a simple group. And the Noether-Castelnuovo tells you, Noether-Castelnuovo theorem tells you that this map, together with this group, they generate the Cremona group in dimension 2 already. So the normal subgroup of sigma is already everything. And this is the same as H. And this one. So the nice maps that we can write down immediately for dimension 2 over C, they don't produce normal subgroups. So it's not straightforward to find them. And a first result, that I know of is by is from 13 by Ganta and Lamy. This is over C, and then by Lonjou over any field in 15. And it says that pure P2 over K has normal subgroups. Okay, and Lonjou even gives an example. You take the map that is an automorphism of the affine space given by x2 to the power of n minus x1, and you want the characteristic of K not to divide n, and you take n at least 2. We don't want it to be an automorphism of P2. And then there exists some power of T such that this power of G generates a normal subgroup that is proper from P2. Okay. And the way they do it, I would like to say something about the way they do it. So what they do is, well, if you blow up P2 in some points, then you can embed the narrow series group of P2 into the narrow series group of S, okay? And you look at the inductive limit of these narrow series groups, and you take the L2 completion. And now the intersection form of P lifts to an intersection form on the narrow series groups of the blow-ups, and it lifts to an intersection form of this inductive limit. And it lifts to an intersection form on the L2 completion. So on here, you have a bilinear form of signature 1 infinity. The infinity is the exception divisors whose square is -1. And if you have that, great, you can cut out a hyperbolic space, which is just the elements. So let's say this is C. In C, the square is 1, and again against the class of a canonic of an ample divisor in P2, it should be positive. You're choosing the upper or lower part of the hyperboloid. And now the Cremona group acts on the space by isometries. And that's great. Now you can apply this sophisticated machinery of small cancellation theory to obtain results like theirs. And now, how do you want to generalize this for higher dimension? In higher dimension, we can construct such an inductive limit, but we won't have a bilinear form anymore. We can have something like a multilinear form, but that is not as straightforward, and you cannot cut out a hyperbolic space in a straightforward way. So what we do is, instead of looking at searching for normal subgroups, we're going to turn around the question, and then we're going to look for quotients of the Cremona group. So now, and we start with a quotient from a subgroup of the Cremona group. So sort of a straight forward quotient would be, if we look at PGO2 of C of X is a bunch of variables. So X is this, or X is this, right? An element in here would correspond to the map X1, X lower bar, going to X1 alpha plus beta divided by X1, gamma plus delta, and then nothing on the rest. So from this group, so this is the subgroup of the of our Cremona groups, and maybe you can put Q in dimension 2, and we have a sort of canonical quotient. We can quotient out by like determinant, and we'll go to C of X star modded out by the squares. Okay, so for our examples that were X1, X bar goes to X1 alpha, X bar, we would send, this would get sent to the class of alpha, that we can now write as a product of irreducible polynomials. And we can now, we get a homomorphism to a sum of torsion groups. And we sum over the prime divisors in P2C or P1Q. And we send this to the sum of the classes of these exponents up to parity. And now we can pick some notion of complicated, and we can project on a part of this sum. I'm sorry. Z2 complicated prime divisors. Okay. Good. So what means complicated? For dimension 2, this means that the degree of the closed point in the support of the divisor is at least 16. And in dimension 3, we're going to look at the curve in the support of the divisor, and we're going to look at the gonality of this curve. So the gonality is the minimal degree of dominant rational maps to P1. So, for instance, the gonality of C is 1 if and only if C is rational. Or, for instance, the gonality of hyperelliptic curves is 2. Okay? And I want this bound to be bigger than the bound on from boundedness. Oh, this cannot be read anymore. Okay, boundedness of Fano varieties. Okay, by the BIP conjecture, by the work of Ricard. Okay, and the theorem now. Pages. So the theorem is that this map here leads to a surjective homomorphism of groups from the Cremona group over C to a sum of Z2 sets, and the sum is uncountable. And this is not restricted. This quotient that I just showed you is not restricted to dimension 3. So you could put this for dimension 3, at least 3. And then this quotient also, if you replace C by Q and X just one variable, you get the same quotient for dimension 2, and you get analogous theorem for dimension 2. Oh, this cannot be read. We got the at least 16, so this is countable. And so she did not only prove this for Q, but actually over any field that is perfect. And that is not R. So the algebraic closure of K has degree bigger than 2 over K. Okay, and I would like to say now that the works overlapped for a bit, and while we could potentially prove the Julia's theorem with the same techniques that we proved this theorem, she proved this with a more elementary method that is more adapted to the plane. So from my perspective, like, it's a very, very nice paper, and I think the fact that it is more elementary, that is more P2, makes it very, very nice to read. So how do you construct such a quotient? What we learned when we were a bit younger was that you take a group and you write, magically you have a representation with generators, and then you have some generating relations. That makes this the quotient of a free group. And then you can construct the map to a homomorphism to another group by just sending the generators onto whatever you want. And what you have to check is that the relations are sent to 1. And this will at once give you that this map is well defined and that it is a homomorphism. And we want to do the same with the Cremona groups, but as we discussed, we don't really know a good generating set of BP3. Not a reasonable one anyway. We can take all its elements as generators, but that will give you very nice relations, but these are hard to work with. And so what we do is we take an even bigger group that contains the Cremona group that that is more wild, but we know a set of generators and we can produce relations. And so our G is going to be, it's not even going to be a group, it's going to be a groupoid. So this is the set of birational maps between rational Mori fiber spaces that are of dimension 3. And right, I'm gonna remind you quickly what is a Mori fiber space. So this is a map, a surjective morphism between normal projective varieties, normal projective with connected fibers. X is Q factorial and terminal, which means that they are nice, they have nice singularities, and they are the varieties that usually come up in the minimal model program. Yuga B has polar dimension than X. The relative picker number is equal to 1, and the anti-canonical divisor on X is relatively ample. So this is one possible outcome of the minimal model program at the end. And right, so now generators, they are provided. And that's by so since we are in dimension 3, I'm going to write QWERTY here, and then this was generalized to higher dimensions by Aiken and McKernan. And it says that this groupoid is generated by so-called circuits of links. Who are these circuits of links? They come in 4 forms. So I'm gonna write 4 diagrams accordingly. So there are special maps between Mori fiber spaces, and the top pointed map is a sequence of log flips. Okay. And then we put on each side of the diagram, we put one Mori fiber space. So we start here, XE over BI is a Mori fiber space. And I want that all the maps here, they are surjective and they have relative picker number 1. I'm going to write it like this. Okay, and the maps, they go from here to here, from here to here. So this is the circuit of link, from here to here, and here is this one. And these are generalizations of what is a circuit of link in dimension 2. So in dimension 2, here we would have the blow up, for instance, of a point. And here this would correspond to an elementary map between conic bundles. So we go from 1 here to the surface, blow up 1 point, and we points, and then we blow down the strict transforms of their fibers. And here we blow down. So this is and then the last one would correspond to the exchange of the 2 vibrations of P1 cross P1. So this is the first projection, and this is the second projection. And you see that on top, I wrote isomorphisms because log flips are isomorphisms in codimension 1. So over in dimension 2, that just means isomorphism. But this is to keep the form of the diagram. Right, so now these, you can see these also, so the Mori fiber spaces are end products of the minimal model program. And you can see these as the representing the 2-rays game, because what is up here is you have a vibration, you have pica rank 1, relative pica rank 1. So here you have pica rank 2, and here as well. And here, the same here, pica rank 1, pica rank, relative pica rank 1. So here you have relative pica rank 2, I'm sorry, and here as well. And the same here. So here you have a rank, relative pica rank 2, and here as well. Okay, so you can imagine you have the 2 ways. You can either contract directly, you can contract directly, you can maybe do a sequence of log flips and then contract, or you can contract to a Mori fiber space, or after a sequence of log flips, you arrive at the Mori fiber space already. So now, who are the relations? I'm going to take back this. So we have Mori fiber spaces. These are relative rank, pica rank 1 vibrations. Now we have the generators of the Biomori P3 that correspond to the 2-ray game, so to rank 2 vibrations. And the relations, they are going to be associated to so-called rank 3 vibrations. So I'm not going to define them because their definition is basically made so that things work out. So it's not a very nice definition. But I'm gonna draw a picture. So we have, it's like one step before the 2-way game. You have a rank 3 relative, a vibration of relative pica rank 3, and then around it, you find, if you start the minimal model program from that rank 3 vibration, you're gonna find a finite amount of options to arrive at the 2-way game. And then this gives you a finite number of circuits of diagrams that you can circle around your rank 3 vibration. And a circuits of these diagrams, they correspond to circuits of links. And so this gives you a relation that sort of circles around a rank 3 vibration. So we call them elementary links. Elementary relation, I'm sorry. Okay, and the proposition that is very inspired by a result of Kalogiros is that any relation between circuits of links is the product of conjugates of elementary relations. Apart from, like, so this means that relations between circles of links are generated by relations, by elementary relations. Okay, so what we have now is that our group, that was Biomori P3, that was birational maps between Mori fiber spaces that are rational of dimension 3. These are generated by circles of links, and the generating relations are elementary relations. Okay, and now you know, a Mori fiber space P3 is a Mori fiber space over a point. So this contains the Cremona group, and we can now construct homomorphisms by sending the circles of links somewhere, and we have to check that this works well with the elementary relation. So this is potentially, this sounds very great, but for instance, it is, if you have an element of the Cremona group, birational map between from P3 to P3. So yeah, what I'm saying now holds in any dimension starting from 2, but what I'm going to explain is just more sort of, I think I can see it easier to see in dimension 3. So if you have a birational map between Mori fiber spaces in general, it is not at all easy to find the decomposition into circles of links, for instance. This is very hard. You can find whole papers of giving you one decomposition. Right? So also dealing with the elementary relations can be hard. They can blow up any, a priori what they blow up is not so easy to quantify. But we have one nice link that we that is a bit easier to deal with. So, and these are links of type 2. I'm going to repeat just in a few seconds what it looked like between conic bundles. These are Mori fiber spaces with the fiber of dimension 1. So a general fiber will be a P1. Okay. So these links, they look like we have our Mori fiber space here, our four Mori fiber spaces here. And this is the circles of link. These are divisorial contractions. And so dimension 3, relative dimension is 1, so this is a surface. And so the exceptional divisor, we can contract it onto something here. So this would be a lemma. So the gamma E, they're curves. So the exceptional divisors, they actually blow down to curves. The exceptional locus of the link are curves. And they project, they are mapped by eta E onto the same curve in the base. And so there exists a curve in B. Okay. And the gamma E's, they are almost everywhere transversal to the fibration of X of the Mori fiber space. and gamma is not in the discriminant locus of B. So in dimension 2, this would correspond to the idea that you're on a elliptical surface and you blow up a bunch of points. You contract the strict transform of their divisors, of their fibers, I'm sorry, and you end up, so maybe you blow up the points, and then you end up with minus on the elliptical surface n minus d. And well, these d points here and here, they're both d points, and they are mapped to the same d points in P1, sort of by construction. And now you imagine this with curves. You have curves that are transversal to the vibration, and you blow up a curve, you get the exceptional divisor, and you can contract, you can do some sequence of log flips, and then you contract a surface onto a curve that is birational to the initial curve that you blew up. So this
Susanna,
being, yes.
we have a question in the chat. I'm not sure
Okay.
if you've seen it, that asks, Carolina is asking, does this proposition, I believe is the proposition before the remark, hold only in dimension 3?
Do you, the proposition about the relations? Which remark was it? So,
Oh,
no,
I'm just reading what she wrote. I don't know
so
what
in
she.
general, what I'm telling you now holds in any dimension over C for Pn in C, but I am telling it to you for dimension 3 because I feel like it is more visual. But you can whenever I say a threefold or dimension 3, just think of your favorite integer at least 3, and go with that dimension. So this is any dimension. Also, for dimension 2, you can do this, but at the end, the quotient that we would construct is trivial for dimension 2. So it's, but you can go with 2 if that's your favorite integer. Okay, so this is.
Okay, thank you.
And then in dimension, right, in higher dimension, you would have to. You still go with conic bundles, so Mori fiber spaces whose fiber is one-dimensional. And then instead of a curve, you would have a codimension 2 variety in here. And then a codimension 2 variety in the base. Okay. It is not at least codimension 2, it's exactly codimension 2. So we don't have a bunch of points here in dimension 3, we actually have a curve. And now, with this, you can define the gonality of phi to be the gonality of that curve, which is the gonality of the two indeterminacy loci, of the indeterminacy locus of phi and its inverse. And in higher dimension, you would have to replace the gonality by something called the covering gonality, which is that in your variety, you have an open set, so that to any point of that open set, there is a curve of gonality, at least something. And then that would be your covering gonality. So there is a generalization of gonality for higher dimensions that is based on the definition of gonality. Okay, so remember that this was the minimal degree of rational dominant maps to P1. And now, so what do I want to do with this? So these are links that look relatively nice, and what we can actually do is describe elementary relations where they appear in. So if we have a link of type 2, between conic bundles. So Mori fiber spaces, whose fiber is of dimension 1, appearing in an elementary relation around a rank 3 fibration T over B. And so we have two options. Either the dimension of B is at most 1, or in higher dimension at most dimension -2. Or you have that B is a surface. So in the first case, it follows what? So I forgot part of the claim, right? So there is some integer, at least 8, such that for any link of type 2 between conic bundles appearing in an elementary relation around this rank 3 fibration T over B, if B is a point or a curve, then the gonality of phi is at most D. And if B is equal to 2 and the curve at which phi is not defined is not rational, then the elementary relation is has a particular form phi 1, phi 2, phi 3 equal to the identity. And so phi 2 is also a link of type 2 between, oh, damn it, right here, between conic bundles. And phi 1 sends the conic bundles involved in phi and the conic bundles involved in phi 2 birationally onto each other. So the conic bundles involved in these two links, phi and phi 2, they are equivalent as conic bundles. And phi 2 and phi, they have birational disequivalence since the curve, the locus curve of each link of phi inverse onto the locus curve of phi 2. So no, I'm sorry. So, and it sends like this. Okay. Okay, so now we are ready to construct our quotient because, so let me remind you, we are Mori, P3, so this is generated by circuits of links and elementary relations. Okay, and we have links of type 1, of type 2, of type 3, of type 4. And I didn't say which one is which, I just told you which one is type 2. Because we don't need it, because we're going to send 1, 3, and 4. We're going to send it to 0, whatever is the group here. And type 2 between Mori fiber spaces that are not conic bundles, we also send them to 0. Okay. And then type 2 between Mori fiber spaces that are conic bundles, where do we send them? So our proposition actually gives us the option to go to a free product of sums of Z2s. And here we have classes of conic bundles. And here we have classes of links of type 2 between conic bundles. It's a bit small, but it's basically the people I've been talking about. And here we can send such a link to, it's represented in this sum. So we're going to choose the factor in the free product that corresponds to the conic bundles implicated in the link. And then we're going to, its class is determined inside that class. We have conic bundles defined at different curves, and these curves give us the classes of the links for different curves. These links are not, for non-birational curves, these links are not equivalent. If we can send between two conic bundles, between two links, if the conic bundles are equivalent, and we can, with this equivalence, we can send the base locus of a link to the base locus of the other link, then they are equivalent. And my definition like this, I send the elementary relations to 0, because if the elementary relation does not include any links of type 2 between conic bundles, I don't care. They are sent to 0 because all their members are sent to 0. And if they include a link between Mori fiber spaces that are conic bundles, then according to the proposition above, they are either of gonality at least bigger than D. So if they have gonality at most D, they are sent to 0. If they are not sent to 0, they're exactly of this form, and things of this form by the propositions are sent to 0. And relations of this form are sent to 0. Okay, and what you have to do now is to check that if you restrict this to the Cremona group, and then to PGL to C of x2, x3, as we did, that this here, actually, that you find a restriction, maybe you have to project onto a sum of Z2 sets. You take the factor that corresponds to rational conic bundles, that you actually get what I claim we get. So you, this would correspond to determinant and then project onto Z2s. Okay, so this is a bit vague. I admit, but I wanted to say a final word on the constant we have here, because this constant doesn't just fall from the sky. So imagine, I'm going to turn this down a little and go back to here. So if you imagine B would be a curve, B is a curve, and then you take the preimage of a point here, you get a surface in x1. And then since this is a Mori fiber space, that surface would be a bits of surface. And then according to our definition of a rank 2 fibration, which is this one, its preimage in here is also a bit of surface. So what you can blow up here is this blow up here, if you restrict it to the preimage of a point here, will be the blow up of at most 8 points, because you have a de Petto surface, you blow something up, you have to stay with it. You have to obtain a de Petto surface, you can blow up at most 8 points. And so this 8 corresponds to a found on a bound for Fano varieties in dimension 2. And similarly, so for dimension 3 and higher, this smaller or equal to D here would correspond to the bound on Fano varieties in general. That was whose existence was shown by Descartes. So maybe I have 8 minutes just to like lay it out, write it. But so instead of having 8 points blown up, you have a fiber that is. You have a curve here. Your fiber is a surface dimension 3 for whatever is in your favorite dimension. And then the D you're looking for is if you embed your fiber into with a multiple of an anti-canonical divisor into Pn, then your D will be the bound on the degree of that Fano variety. And you can bound it for any dimension. You have this bound universally for Fano varieties. Okay, so this is just to say that this bound here in the proposition is highly non-trivial. Right, I've said everything I wanted to say, and I'm happy to hear your questions. I'm gonna put up my video screen again.
Thank you, Susanna. Any questions?
Thank you. Sorry, I got a phone call at the same time. Are there any questions you want to put them in the chat, or you can speak directly?
Yeah. I did not respond to a lot of questions during the talk. I felt a bit overwhelmed by checking the questions. So if I have not answered any questions that you would post during the talk, please post them now.
I think the only question was the one I asked you. And then someone was complaining about the handwriting, no, the quality, but everyone else was fine. So,
Susanna, I have small question. So, for example, if you consider this problem for birational automorphism group of just threefolds,
yes.
So you can, it's enough to consider ruled, uniruled threefolds, yeah, Kadari dimension negative. And can you get some general answer for threefolds, what the answer should just be in general?
So
all
what
split in two cases.
Yeah. So the quotient the quotient that is here, you can construct it for any variety that is birational to a Mori fiber space. But then the question is, what is it? Does it restrict to something non-trivial on your favorite group? So you can show that it is non-trivial for certain conic bundles that are decomposable. But other than that, I don't know if you can if you can always say this is non-trivial. That would depend on your threefold. I don't know if it's true in general for threefolds, for instance.
No, in general it should not be true, because there's, for example, this birationally rigid threefold such that this group may be trivial. The whole group of birational automorphisms, but maybe it's possible.
Yeah, you're right. I mean, if the whole birational group is isomorphisms, it is going to be zero, but trivial.
Maybe it's possible to get a general answer, like for which threefolds, say this group is something like.
I mean, that would be great. Yes, I guess there is some hope for threefolds because I have the impression that threefolds are well studied. So there we should be able to find something to find the non-trivial homomorphisms for these threefolds.
Thank you.
Thank you. Are there more questions? No? Okay, so maybe I'll pause the recording.